Rahul Mukerjee from the Calcutta Institute, from the India Institute of Management at Calcutta. Thank you.
Thanks. Do you hear me? Okay. First of all, I must thank the organizers of the conference for their very kind invitation, and this is a joint work with Tathagata Banerjee from another Indian Institute of Management. Well, we have a system of Indian Institutes of Management. So, he works in the western part of the country. So, I will be talking on factorial designs and some existing results and some open issues. Now, for designs, here are some early references: Kerr and Churchill, 2001, Young and Speed. They discussed factorial designs. This is in Nature Genetics Supplement, and I guess that is one of the earliest references, if not the earliest, in factorial designs for microarrays. And then there is Churchill, 2002, Nature Genetics Supplement. Now, in factorial designs, two kinds of parameterization can be thought of. The first one is very well known, namely the orthogonal parameterization. When you look at, you define contrasts through orthogonal linear combinations of the treatment parameters. For example, the main effects are orthogonal to the interactions. And then we can also think of orthonormal system within each factorial effect. For example, if some factor has say 3 levels, then we can describe the effect of that factor via 2 mutually orthogonal or orthonormal contrasts. And in the context of microarrays, optimal designs under orthogonal parameterization for factorial designs were studied previously by Kerr, 2006. And there are several other references, and one also I just located. This is by Grossman and Schwab, 2007. This was when I located it, it was available in the form of a preprint. Maybe it is already published. Now, as opposed to the orthogonal parameterization, there is another parameterization, namely the baseline parameterization, and I am soon going to describe this baseline parameterization in some more detail. And some early references, well, even Young and Speeds, they introduced this baseline parameterization, and they have some broad discussion on it. And Glonick and Solomon in 2004 biostatistics obtained elegant computational results on optimal designs under the baseline parameterization, but all their results were computational, no theoretical result. And well, this inspired us to look into to look at the paper by Glonick and Solomon in some more detail, with a view to obtaining theoretical results, providing algebraic justification for some of their computational results. And this appeared in 2008 in the Annals of Applied Statistics. And in today's talk, the results that I am going to describe are mostly based on our 2008 paper, to be followed by a statement of some open issues on optimal designing under the baseline parameterization. I am soon describing in some detail the distinction between the baseline parameterization and the more common orthogonal parameterization in factorial designs. So, what is done here? The first thing is main thrust would be on the baseline parameterization, and we will try to get analytic as opposed to computational results, and we will discuss some open issues. Now, some points to note. First of all, in a baseline parameterization, the contrasts are quite different from those under orthogonal parameterization. So, although a lot of results are known under the orthogonal parameterization, those do not immediately lead to corresponding results under the baseline parameterization. And now, this baseline parameterization can be natural in many practical situations. It is just like it is quite analogous to control versus treatment in varietal designs. So, if we look at a factorial design with baseline parameterization, then that gives us a multi-factor extension of the control versus treatment. And in a recent paper, Kerr, in 2006, I think that was in the Journal of Quality Technology, she discussed some situations when the baseline parameterization is appropriate and some other situations when the orthogonal parameterization is appropriate. Broadly speaking, the baseline parameterization is natural when for each factor there is a standard baseline level. For example, in the 2006 paper, Kerr gave an example of a toxicological study when there can be several toxicological components and, well, the presence of each toxin is the non-baseline level and the absence is the baseline level. And, well, although we are stating our results in the context of microarrays, they can be useful in other contexts as well, when for each factor there is a natural baseline level. For example, in an industrial process, there can be several settings. For each machine, there can be several settings. Now, the setting that is being currently used can be thought of as the baseline level, and the other possibilities represent other levels associated with that machine, each machine representing a factor. Now, basically then what we are going to describe here is a factorial counterpart of the control versus treatment experiments, which and a nice review of this, though now slightly old, is available in the Handbook of Statistics volume 13 by Dibben Majumdar. Now, one point I must add here, that the baseline parameterization looks simpler, but mathematically it is harder to handle compared to the orthogonal parameterization. The reason is the basic entities of interest are themselves non-orthogonal. So, we cannot use tools of orthogonality, and as a result, even in the traditional factorial design literature, almost nothing is known under the baseline parameterization. Let me give you a quick example. If I work under the orthogonal parameterization, then for fractional factorial plans, it is well known that under wide generality, plans based on orthogonal arrays are universally optimal. But under the baseline parameterization, no counterpart of this result is as yet known to the best of my knowledge. Now, we look at the simple case 2 by 2 factorial considered by Glonick and Solomon that motivated the present study, and with reference to this setting, this very simple setting, we define the baseline parameterization that we were talking about. Now, we have two factors, four treatment combinations, the associated treatment effects being denoted by tau naught naught, etc. Now, we define the 0 0 is taken as the baseline treatment combination. So, for each factor 0 is the baseline level. So, tau naught naught is the baseline effect, then tau 1 naught minus tau naught naught is the main effect of the first factor, similarly the main effect of the second factor, and finally, the interaction effect between the two factors. The point to be noted here is that for the two factor setting, the interaction, the definition of interaction is the same as under the baseline parameterization. The definition of interaction under the baseline parameterization is the same as that under the orthogonal parameterization. However, the main effects are defined differently, and it is obvious that theta 1 naught, theta 1 1 and theta naught 1 and theta 1 1 are not mutually orthogonal contrasts. This will complicate matters, and the parameters of interest are theta 1 naught, naught 1 and 1 1 representing the two main effects and the interaction. And this definition of the main effects and interactions is exactly as in Glonick and Solomon's 2004 paper, or in the paper by Young and Speed in 2002 in Nature Genetics Supplement. Now, what is our design criterion? We think about a W optimality criterion, which is a generalized version of the A optimality. The notation we describe here, the V naught 1, V 1 naught, these are the variances of the respective best linear unbiased estimators, and the two main effects are given the same weight plus W times V 1 1, recognizing that the interaction may have the degree of importance of the interaction may differ from that for the main effects. In particular, Glonick and Solomon noted that W can be greater than 1. The two-factor interaction can be more important in applications than the main effects. But for the time being, we are just keeping W general, and our results hold, most of our results hold for W greater than equal to 2 by 3, which means that even if you take W equal to 1, the results should go through. Now, we make some assumptions. First of all, only biological replicates, there is no technical replicate. For the time being, we assume this, which in turn implies that observations from different slides can be assumed to be uncorrelated. And homoscedastic, that we are also assuming, I am coming back to this point later on, and no dicolor bias for the time being. The only design constraint concerns the number n of slides. We are not taking into account the fact that the samples corresponding to different cell populations may not be equally expensive. This is precisely the setting of Glonick and Solomon, because this work was primarily motivated by the objective of providing some theoretical basis to the findings in Glonick and Solomon's paper. So, for the time being, we are making these assumptions, and later on we will come back to these points. Now, for the 2 square that was considered by Glonick and Solomon in full detail, there are 6 possibilities for any slide. If I ignore the dicolor bias, so 0 1 and 0 0 means a slide where I am comparing 0 1 and 0 0, forgetting about the dicoloring. If I take care of the dicoloring, I will get 12 possibilities instead of 6. Now, we first apply the approximate theory, because the design space here consists of only 6 points. So, using the approximate theory, it is not hard to find the optimal design, and we denote a typical design measure by pi, and pi I is the proportion of slides that correspond to the ith of the 6 possibilities listed above. Then we get, this is our first result, that if we define xi in this way, and then this design measure is W optimal. W optimal means weighted A optimal, where the interaction component receives weight W and the 2 main effects receive weight 1. Then this design measure is W optimal whenever W is greater than equal to 2 by 3, under of course the baseline parameterization. Now, one point to be noted here is that in the optimal there are 2 zeros. You can, and we get 2 zeros even if W equals 1, and one can readily see that if instead of the baseline parameterization one works under the more common orthogonal parameterization, then at least for W equal to 1, the optimal design measure should be 1 by 6, 1 by 6 up to 1 by 6 uniform design measure, which corresponds to the balanced incomplete block design. If one works under the orthogonal parameterization, then one can show that at least for W equal to 1, this should be uniform 1 by 6 everywhere. So, this shows that under the baseline and orthogonal parameterization, the objects of interest are different, and as a result the final optimal design measures can also be entirely different. Now, I am skipping the details here, and the detailed proof is available in the website of the Annals of Applied Statistics. The editors advised us to delete all the proofs from the paper. So, so there is no proof in the paper, only in the website. Now, there are some related references where approximate theory was used in the context of microarray experiments. One is Buenafil-Ho et al. In genetics, and Grossman and Schwabe, but their settings, criteria and final results were different. As far as I recall, in the paper by Grossman and Schwabe, they worked under the orthogonal parameterization and assumed the absence of some of the interactions. But here, at least in the 2-factor case, we are not assuming the absence of any interaction. Now, from this result, we can get exact designs also by simple rounding off. We can round off the design measure and get the exact designs, and these designs, when I compared them with the optimal approximate design measure, they have 97% and often 99% efficiency. And since the optimal approximate design measure is actually unattainable, with a finite number of slides, we conjectured that all these are W optimal. And from these approximate theory results, we also get theoretical justification for many of the computational findings of Glonick and Solomon. For example, a W optimal design has to be admissible in the sense that there is no other design that dominates the W optimal design with respect to every factorial effect. And Glonick and Solomon's main thrust was on admissibility, and many of their admissible designs, the admissibility of many of their designs follow from this W optimality. Now, their counterpart of this result under orthogonal parameterization is this. And as you can see, for W equal to 0 to 4, this happens, and in particular if W is 1, then this pi naught orthogonal reduces to 1 by 6, 1 by 6, etc., which is just the balanced incomplete block design. So, what we learn is that even in the simplest case of a 2 square factorial, the baseline parameterization may lead to optimal designs which are entirely different from the balanced incomplete block design. So, intuitively we feel that if there exists a balanced incomplete block design for paired comparison with block size 2, that should be the best design, but we cannot use such a balanced incomplete block design blindly when we work under the baseline parameterization, and hence the objects of interest are quite different from those under the orthogonal parameterization. Now, we turn to general factorials. Now, we look at general S1 by S2 by Sn factorial, continue with the baseline parameterization, and design space now can be too large to apply the approximate theory. You know, for example, if you look at say a 3 by 3 factorial, then there are 9 treatment combinations. So, how many possible slides? 9 choose 2, that is 36 possible slides, even ignoring the dye color bias. So, we did some trial and error using various algorithms for approximate theory, but nice results were very hard to obtain. So, we tried the combinatorial tools, and 2 combinatorial tools. Well, the second one is not really a combinatorial tool. 2 tools we are using. One is the Kronecker calculus. This is quite popular, though an old method in the context of factorial designs under orthogonal parameterization. We look at a version of the Kronecker calculus which is useful under the baseline parameterization, but the main tool for proving results is that of unimodularity. What is unimodularity? A unimodular matrix is one whose all minors are 0 or plus minus 1. And unimodular matrices are useful, for example, in handling transportation problems in operations research. They show that if the original basic feasible solution is integer valued, then all subsequent solutions are also integer valued. Now, using unimodular matrices coupled with a notational system based on the Kronecker calculus, we could prove some theoretical results, and we are not making any assumption about the absence of any interaction, and as a result the minimum number of slides is V minus 1 under the absence of under the absence of dye color bias. Now, we first look at the saturated case, n equal to V minus 1, and the notation is described here, and rho I1 IN is obtained by replacing the first non-zero entry of I1 IN by 0 and leaving the other entries unchanged. For example, with a 2 by 2 by 3 factorial, if I look at the treatment combination 0 1 2, then rho 0 1 2 is 0 0 2. What is happening? The first non-zero entry 1 is being replaced by 0. Similarly, here 1 1 1 becomes 0 1 1, and then we get this result using unimodularity and the Kronecker notation. If n equals V minus 1, then this design simultaneously minimizes. This simultaneously is very important. It is much more than the standard optimality criteria like A, D, E or W. It simultaneously minimizes the variances of the blues of every object of interest. This is a very strong result, because optimality is achieved separately for each parameter of interest. And you can see, if you look at the definition of rho, this is asymmetric in the factors. So, the optimal design is non-unique. If I permute the factors, I can get more optimal designs, not just one, and this can be used under resource, this can be useful under resource constraints. By factor permutation, one can get many more designs, and for n equal to 2, actually there is a broader class of optimal designs. I can define rho I 1 I 2 as either 0 I 2 or I 1 0, leading to a collection of 2 to the power s 1 minus 1 times s 2 minus 1 optimal designs. But all these results concern the saturated case, leaving no internal degrees of freedom for error, which is undesirable for testing of hypothesis. So, next we pass on to nearly saturated designs, and here analytical results are as hard to obtain as any application of the approximate theory is. So, what we do, we describe a heuristic approach. We look at the optimal saturated design, and then broadly speaking we look at all possible augmentations of the optimal saturated design for a given number of runs and pick up the best design under the chosen criterion. I repeat, we first list all optimal saturated designs, then look at all extensions thereof, and out of all such extensions pick up the best one under the chosen criterion. And for n close to v minus 1, these steps are much easier than to implement than a complete enumeration. Now, we examine how efficient this ad hoc procedure is. Now, for this, what are the least favorable situations? The situations where the saturated design itself is very small, and as a result adding only 2 or 3 slides can have a significant impact. If the saturated design has say 30 slides, then adding 2 or 3 slides will not have a major impact. But if the saturated design itself is small, then further addition can have a significant impact. From that perspective, the worst, I mean the least favorable situations for this augmentation procedure are the 2 by 2 and 2 by 3 factorials, and there we checked that if 1, 2 or 3 additional slides are taken, then this method, the heuristic method, actually gives us the optimal design. I mean the optimal design was obtained by complete enumeration in these cases, and then again by the heuristic method, and these two agreed. Now, model with dye coloring effect, and here we looked at the most general model. Dye coloring is treated as a separate factor which may possibly interact with the factors of interest. So, there are 2 results here. One is we then require at least twice v minus 1 slides, and for n equal to 2 v minus 1, the dye swapped version of the previous d naught, I mean the d naught was the optimal design for the saturated case, the dye swapped version of d naught would again simultaneously minimize, simultaneously is important, the variances of the blues of all parameters. So, this in a sense vindicates a suggestion in the paper by Young and Speed 2002 in Nature Genetics, and well, these 2 results, the proofs are quite lengthy here, because the possibility of non-orthogonal estimation complicates A. Then why should we require twice v minus 1? After all, the dye color factor is a nuisance factor, and there may be non-orthogonality that complicates the proof of A, and the proof of B is also involved, because orthogonality alone does not guarantee optimality. Orthogonality alone does not guarantee optimality with twice v minus 1 slides. So, in a sense B vindicates a proposal by Young and Speed, and again we checked that if you look at nearly saturated designs in this case, then the same principle of augmentation would work well. Now, some open issues quickly. So, finding more theoretical results, this one is a bit the notation is quite heavy. For S 1 by S 2 factorial with no dye coloring effect, a specific problem was posed in our paper, and all numerical studies indicate that this conjecture should be true. The conjecture is like this. I think I have just 5 minutes left, so let me proceed a bit faster. The conjecture is available in the published paper, and we had some numerical evidence in support of the conjecture. So, one open problem is getting more theoretical results. Then comes the very important question of fractional replication, and traditionally in fractional replication we assume the absence of interactions. In microarrays we are not sure from what stage we can assume absence of interactions. For example, Glonick and Solomon note that the two-factor interaction can be more important than the main effects. Then do we abruptly assume that interactions involving 3 or more factors are absent? I do not really know. So, with more concrete suggestion from the biologists or the actual experimenters, probably we can make some headway with fractional replication problems using some of the techniques developed here. And then we assumed for the dye color bias, we assumed that the dye color is a separate factor which can possibly interact with the factors of interest. We do not do that. We represent the dye color bias by just one parameter, one additive parameter. Then the situation is like that in says biased spring or chemical balance weighing designs, and this problem was considered by Carr and Churchill in some detail in this case, and this result is very important. Any event design allows a dye color assignment that ensures orthogonality to eta, the one parameter representing the dye color bias. So, this result may be combined with some of our results to make further conjectures under this simpler model, but this is again one needs to investigate this. A fourth problem considers robustness. Robustness means for example, the biological variation, the measurement error vis-a-vis biological variation. Now, if we assume that the biological variation is the same for all cell populations, and furthermore there is no technical replication, then all our assumptions like homoscedasticity and zero correlation, they go through, all the results go through. But if the biological variation corresponding to the cell populations are not all equal, then the problem becomes very complex, and we did some robustness study of our results, and it is seen that most of our results remain quite robust. Now, the next question is very important, biological versus technical replication. Now, you know, technical replication can lead to correlation among data arising from various slides. Now, if I assume for a moment that biological and technical replications are equally expensive, well, this assumption may itself be debated. Then the design problem, and of course, we further assume that the correlation, we pretend that the correlation induced by the technical variation is sort of known, as is done say for example, in repeated measurements designs or similar other contexts in developing optimal design theory. Then even then the problem becomes quite complex. For example, if I have say a design where each treatment combination, a 2-square design where each treatment combination is replicated twice, then that design can lead to 16 designs, 2 to the power 4 designs, depending on whether the replication for each treatment combination is biological or technical. So, we made a complete enumeration for 2-square, only for 2-square design, and that too with only 4 slides, and then it was seen that this design with all replicates biological is W optimal whenever W is greater than or equal to 3, and optimal in a very strong sense irrespective of the correlation induced by technical replication, if any. Of course, this complete enumeration is unrealistic for more general factorials. So, we need some theoretical procedure here too, and if the cost of the biological replication is non negligible, then the problem becomes even more complex, because some kind of cost function has to be brought in. That is all that I have to say. Thank you very much for your patience.
You mentioned at several stages that we do not assume any interactions to be absent. But would you estimate also, say for instance in 2 to the 4 model, the 3-factor interactions, or only do it as in the Kerr 2006
I understand. See, our theoretical results regarding optimality, they say that all we are getting optimality with respect to each parameter representing each interaction. Now, if the user says that, well, that kind of optimality is not needed, then well, we cannot reduce the size of the experiment. You know, unless I assume the absence of some interaction, I cannot get less than v minus 1 slides. I cannot get, probably I cannot get, provided, okay. But if you say that some interactions are possibly there, but I still don't wish to estimate them, in that case, yes, I can. In that case, yes, I can. But no theoretical results seem to be known as yet. Yes?
Is there some model robustness of your designs? For example,
Yes.
your example is on a main effect and two-factor interaction model.
Mm-hmm.
And if the two-factor interaction is not there, will the design still be optimal for main effects only?
Given the possible non-orthogonality, this is a good question. I have to check this. Yes.
You had a specific criterion in
Yes.
the two-factor situation. But when you move on to several factors, what is your criterion?
Okay. With multiple factors, with two factors, we have equal weight for the main effects. For multiple factors, the criterion could be like this, although in our numerical studies we didn't include that. For the main effects, weight 1, 1, 1, say I have a 2 to the power n setting. Then for the main effects 1, 1, 1, maybe for the two-factor interactions W1, 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 for the three-factor interactions W2, W2, like that. But we didn't explore this in such detail here, because in the numerical studies we looked only at the two-factor settings, 2 by 3, 3 by 3, 4 by 4, like that. And for the unsaturated case, and for the saturated case, we are having optimality separately for every parameter. So the question of combining didn't arise. Incidentally, as a partial response to your question, in most of our studies, we looked only at the two-factor setting, which is why the question of assuming the absence of the interaction didn't arise, because we followed the setting of Glonek and Solomon, who said that the two-factor interaction is even more important than the main effects. But of course, the question that you were, from a purely mathematical standpoint, is a very good question, and we have to explore this. Estimability will be there, of course, but optimality I am not sure, because of non-orthogonality of the parameters. They will not be optimal, perhaps. Yes.
Last question from Steve.
If I understand correctly, your W optimality for this parameterization is equivalent to some kind of L optimality for the orthogonal parameterization. So I wonder, are your results more general than you're stating?
Well, if I look at my objective function here and translate that to the orthogonal parameterization, it will, of course, this will be in the form C prime sigma C, where sigma is the dispersion matrix under the orthogonal parameterization. Certainly it will be like that. But the question is, if I stick to the orthogonal parameterization, then this C vector may not have any natural meaning. For example, if you think that the orthogonal parameterization is appropriate, then you may not like to use these results, because you are getting optimality under some criterion which may not be very meaningful under your chosen parameterization.
But the two,
Certainly we can express it, C prime C sigma C.
or wouldn't the two optimization problems be the same? They would be equivalent.
But the trouble is that this is like some kind of C optimality under orthogonal parameterization, and there again, for arbitrary C, you don't know exact optimal designs.
Let's thank all the speakers.